242, Newton's first law. We're going to look at all of Newton's laws. Today we're specifically looking at the first law. Okay, the first law. First, we're going to talk about the correlation that exists between the motion of and the net external force on an object. And we mentioned this yesterday, but we're going to specifically talk about these correlations today. Second, we're going to talk about what the net external force is acting on an object. And third, we're going to analyze problems when forces are balanced in what's called the state of equilibrium. Where have you heard equilibrium before? You've heard it. Biology? Where else? Chemistry. Give me specifics in those classes where you've heard equilibrium and how they relate to science. Go ahead.
Like in biology, like diffusion stuff, equilibrium.
Yeah, so you have osmosis, right? So imagine you have a cell membrane and there's a certain concentration on one side of the membrane and a certain concentration of another fluid. It needs to find a medium or a standstill or a level point, like a seesaw. When a seesaw is even, that's equilibrium. That's exactly what you're doing when you look at equilibrium. You're balancing forces in physics. You can do it in chemistry also when you balance equations. You look at what's called chemical equilibrium, right? Where you put coefficients in front of the molecules to determine the amount of particles that were changed. So you have to put a coefficient so you balance the amount of hydrogen or oxygen atoms on each side of the equation. Same thing applies here. But now we're looking at forces, and believe it or not, it's a lot easier, okay, when it comes to equilibrium. It's just a matter of adding and subtracting numbers. That's all it is. Okay? So let's go on. Let's take a look at Newton's first law. Can I get someone to read, please? Nice and loud. Newton's first law. Lisa, go ahead.
An object at rest will remain at rest, and an object in motion continues in motion at a constant velocity unless acted upon by an outside force.
Okay. What is the... Very good, thank you. What is the common term that we use to describe Newton's first law? Law of inertia. Good. I heard it twice. Inertia. You should write that down, obviously, okay, if you didn't know that. If you know it, sure. But again, this is also called the law of inertia. The law of inertia. Okay, so this is where, I know a few of you have already talked to me about that movie Gravity, the idea. This is what it is. When Sandra Bullock, kind of floats into space, there's no gravity acting on her, so the movie should really be called Lack of Gravity. But the fact that there is no gravity acting on her, she continues to float into space because, look, it says, an object in motion continues in motion at a constant velocity. So if I were to just go like this to Gio and just tap him, he would float away forever and ever if there was no force acting on him.
I'll catch you.
Thankfully, and so would I. That's a good point. And we'll talk about what's called momentum, and that's where momentum comes in. I would also move, unless I was somehow fixed to some object, right? Okay? An outside force. What is an outside force? What does that mean? You hear it all the time, but most students have no idea what an outside force even is. What's an outside force? What's an inside force? Does an inside force exist? What does that even mean?
An outside force means that it's not exerted from the person, but it's exerted upon the person.
That's exactly right. You all hear that? An outside force is not exerted by the object, but on the object. Very good. Well done. A force that's exerted on the object. So, for example, I'm driving my car. If I want to stop, I apply the brakes, right? The brakes are an outside force acting on the car, causing it to stop. What else causes the car to stop? We've talked about this a few times. Friction. Yeah. Air resistance, friction slowing it down. Now, friction between the tires also causes the car to go when you accelerate. Because you hit the gas turns the axle turns the tire friction between the road pushes the car forward, actually. If the car spins too fast, what happens to the tires? They burn out or they slip. It's called a non-slip condition. Well, the tires, if they spun too fast, if you ever see somebody get in a car and they nail the gas, they just hit the gas, what happens? You see the tires spin in the back and then it catches and then it goes. Okay? The tires burn out, and that's what will happen. Because there's too much velocity, it's overcoming the friction that's there. Remember that friction we were talking about in the lab? That you needed a certain amount of friction to get the file cabinet moving? Just to get it going? Well, when you spin out, you're overcoming that friction, which is causing it to slip or slide.
Is that how you drift? When there's a velocity of the wheels greater than the friction?
I don't know what drifting is, to be honest. I've heard the term. One person.
Basically, like, you actually do that same thing, but only to get the wheels to let go. Once they have, you don't need to spin the wheel anymore. It'll just slide out.
In drifting, there's no traction between the tire and
Yeah,
the floor, or like there's no friction, I guess, while you are turning, and then therefore you get a certain type of turn.
And allows the car to like fishtail out a little bit.
Yeah. It just kind of slides.
Yeah. So that's exactly what it is. Now, here's the question though. It's a combination really, because when you drift, it's when you're turning, right? Yeah, it's a combination of you moving in rotational motion and the tire spinning. It's not just the tire spinning. It's both, for sure. Okay? All right, that's Newton's first law. Let's take a look at the next slide for a moment. So when we talk about what's called a net external force, we really mean what's called the resultant. The resultant. So, I gave the example yesterday. If I were pulling on the desk for a little while with a force, the desk is pulling back with the same force because it's not moving. But the minute I can overcome the force that the desk is pulling back with, it'll start to move. You did this in the lab. You could push the file cabinet for 100 newtons. It didn't move when there was friction. You could push for 200 newtons when there was friction. It didn't move. It wasn't until you exceeded the friction force, the maximum static friction force, that it started to actually move. That's looking at the net force. So if I push on this table, the net force is 0 because it's not moving. It's balanced. But if I pushed on Gio's chair and he slid forward, the net force would be in that direction because he's moving in that direction. Okay? Does that make sense? It's overcoming another force. It's having a non-equilibrium. When there's a net force on the object, there is not equilibrium. But when the net force is 0, you are at equilibrium because everything's balanced. Okay, everything's balanced.
So you could be pushing on a force on like an object, but the net external force could still be 0.
Correct. The net force, not net. Well, yeah, net external. We'll say, yeah, net external. Absolutely. Okay. So the idea again, though, is that you have a balance of forces. If you don't have a balance of forces, then the object moves. That's what causes acceleration. We talked about the fact that force is defined as the cause of an acceleration, right? So if there is an overall net force, there is an overall net acceleration, which is why Gio moved. But the desk didn't move because there wasn't a net force. It was balanced. It was completely balanced. So there was no acceleration. Okay? Let's take a look at example 1 to make sense of this. Go ahead, Julie, first.
You said when there's a net force, like if there is one that's greater than 0, there's no equilibrium, or there is?
When there is a net force, meaning there's no balance going on, you're not at equilibrium. Okay? When there's a balance, you're at equilibrium. Okay, remember, equal means the same on both sides. That's the idea of equilibrium and balance. So the first one, let's take a look at. Very simple problem, okay? And you're going to see when you have this on like a test or anything, it's a really easy one. But because we haven't done it yet, let's take our steps and go through this one at a time. First, a crate is pulled to the right with a force of 82 newtons, to the left with a force of 115 newtons, upward with a force of 565 newtons, and downward with a force of 236 newtons. Find the net force in each direction. So imagine an object in the middle of space, just sitting here. And then suddenly, forces acting up, down, left, and right are pulling on it. That's what's happening here. It's not on a floor. It doesn't say it's on a floor. It doesn't say it's on a surface. So what we're going to do is just draw an object in the middle of space. And we're just going to draw 4 external forces coming from it. Okay? It's being pulled in every direction right now. Now, we always say that the object being pulled has a force applied to it of Fp. Remember Fp from yesterday? Pull or push. But I can't put Fp for all of these, right? So we need to really specify what's going on here. So instead, if you want to, you can write like F1x and F2x, because those are in what direction? The x direction. We can call this F2y and F1y. It doesn't matter as long as you specify. Is that clear? I'm picking these subscripts right now to indicate that this is the first force in the y direction. Well, this is the second force in the y direction. This is the first force in the x direction and the second force in the x direction. It does not matter really. Okay? If you wanted to call it FP1, FP2, FP3, FP4, for the 4 forces that are applied, that's absolutely fine. It makes no difference. But what I want you to know is that they need to be different, okay? You can't call them all FPs, because then later on, when we start writing equations, it's not going to make any sense. You're going to have FP minus FP. It just looks like 0. But in reality, these are not all the same. So give some sort of signal that they're different. Okay, list their givens on here. Well, actually, for now, let's leave it. Let's leave it. We have our free body diagram. We'll leave that alone. Let's use the values in our equation. So, if we want to find the external force in the x direction, what do I do to those two values? Again, it's not meant to be difficult. Okay, it should be just pretty basic answer. Yeah. So F1x is what value?
82.
Minus 115. Okay. So this is the net force in the x direction. I'll move it up so you can see. Okay, so again, F net in the x direction is F1x minus F2x. Why is it minus again?
Because find the resultant.
Okay, but the force is applied in what direction?
The left.
Yeah, okay. So
Yeah.
that's why it's a negative in front of F2x. If they were both being pulled to the right, what would you do? You would add them together, right?
Yeah.
It'd be like two people pulling on the same desk. They would be helping each other out, as opposed to one person pulling and one pushing in the other direction. I saw a hand go up. Did the question get answered? Okay. So we have 82 for F1x, that was to the right, and 115 to the left. Subtracting them, we should get 33 negative? I'm going to go off the screen for a moment, sorry.
So I have a question. Would you just take the absolute value?
No, because now we're looking at a force, and the negative indicates that the force applied left was greater than the one to the right.
Okay, but how do you decide on your free?
Same as velocities, exact same way we did. Left is negative, right is positive, up is positive, down is negative.
So why would it be 82 minus negative 115?
This negative sign indicates that we're going to the left. The 115 is the magnitude of the force.
Oh, okay.
Okay, if you wanted to, you could put a plus, a negative, that's fine. Look, you can do this. Okay, that's what you're saying, really. You can add the two forces together, we call this a negative, but in the end, you still get the same answer. Alright?
How do you know which one goes in the beginning of the equation?
Doesn't matter. If I switched them, I could have written it like this. Okay, I could have written negative F2x because it's going left, and a positive F1x because it's going right. You would end up having negative 115 plus 82. Same exact answer. Okay? Either way is fine. I'm going to erase that just not to confuse people though, okay? Alright. Let's go to the y direction now. In the y direction, what do I have?
565 and negative 236.
So it was really F1y minus F2y. Again, the subscripts I made up. So please do not go home, listen to me folks, don't go home and memorize these equations right here. For forces, you're never really memorizing equations. You're coming up with the equations based on your free body diagram. Is that clear? You are never, ever memorizing these equations. Ever. It will just cause headaches because every problem is different. What if I suddenly have another force acting at an angle and another friction force? Things change, okay? So don't memorize. Look at the diagram. Look at the free body diagram. So F1y was acting up, so that gets a positive. Y was acting down, so that gets a negative. So positive 565, negative 236, giving me 300. God bless you. 329 newtons. Okay, 329 newtons. Now, here's a question for you. What does this mean? Where is the object going to move overall? Look at your two answers. Look at your net forces. Yeah, up and to the left. Take a look. It's moving left with a force of 33 newtons, up with a force of 329. So which way is it really moving? Which one's bigger? Yeah, up. So we have something at like a high angle, like a 70-degree angle. Remember when we did velocities and initial velocities? If the angle was bigger than 45, it was mainly in the y direction. Same idea here. Look at the y direction. It is so much greater. So here's what I'm going to do. I'm going to draw something for you. Draw negative 33 newtons from here. Just draw to the left, 33. And then draw up 329. So go to the left 33 and then go up 329. This is not drawn to scale, clearly. Everybody can see that, right? Okay, it is not drawn to scale. Then connect those two. This is what's called your resultant vector.
Pythagorean Theorem.
Yeah, very good. And if you want to figure out what the resultant vector's magnitude is, or its value, you can just simply use the Pythagorean Theorem to figure it out. Notice I ignored the negative 33 because I went to the left. So I didn't have to write negative in front of it. Okay? I'm just putting the positive values because we're looking at the three triangles. Now, if we're able to find that value of the vector, use the Pythagorean Theorem. How can I find the angle? You guys have done this in trig now in math. I noticed I talked to Ms. Starks.
Well, you'd have to
You did.
the inverse.
Yeah, you're going to end up using an inverse function. So once you get the three legs of the triangle, either decide what you'd like to do, tan, sine, or cosine, but you're going to use an inverse function to get theta. And this is theta right here. Remember, theta is always between the vector and the horizontal axis. This is your theta right here. So let's go ahead and find r and find theta together.
Technically, wouldn't the angle on top also be between?
Sure. If you were to go like this, put a dashed line and find that angle right there, that is also. This is definitely not theta. This is 90 minus theta. Okay? Remember, if I call this theta, these two have to add up to 90 because it's a right triangle. So this is 90 minus theta. This is theta. This here, if you put a line here, this is also theta. Okay?
Are we trying to find the angle or the resultant vector?
We're really trying to find the resultant vector, but I'm also going to talk about the angle right now. So let's find the resultant vector.
That'd be like two different types of problems. Where it's like A, find this, and then B.
I would say find the magnitude of the resultant, and then find the direction of the resultant. The magnitude is the value we're getting now, and the direction would be theta. What do you get? What do you get? Come on. Nobody did this? Alright, so we get, I'm not stopping and waiting, guys. We're running out of time if you're not going to do it. We get 331 approximately. Approximately 331 newtons. Now, what do you notice? That is not much bigger than 329. Take a look. This was 329. Why did this not go up by too much? Because 33 has very little significance when squared compared to 329 squared. 33 squared is around 900 something. 329 squared is a much larger value. This significance outweighs this so much that it barely moves it up at all. So that is the resultant vector, 331. Okay, it is very, very, very close to the y direction because this is mainly in the y. So now I've got that direction, or I've got that number. How can I find theta? This is theta, this is adjacent, this is opposite. We've got adjacent, we've got opposite. What function can I use?
You use cosine, inverse.
Please use the ones that we have just for now. Don't use the r value.
So you could do inverse and tangent.
Good. So tan theta equals opposite.
So it'd be 329 over 33.
Good. So theta equals tan inverse of that. Okay, again, opposite, adjacent. Opposite, adjacent. 329 over 33 is what tan theta is. So to get theta by itself, tan inverse it, move it over. Okay, take the tan inverse of 329 over 33. What do you get for theta? Should be a very high number, close to 90 or much well above 45. Thank you. 84.3 degrees. Okay? So we could say the following as our answer in a verbal form or a verbal statement. The resultant is 331 newtons at 84.3 degrees northwest. And make sense of that answer, please, in your mind. Picture this. Northwest. Here's north. Here's west. That's the direction we went, wasn't it? Okay? And this is at 84.3 degrees north of west. That's what that really means. It is north of the west angle. And I'll show you. If I went directly to the left, this is west. But I'm above that, so I'm north of west. That's what that means. So 84 degrees north of west. This is giving me the angle I am above west. Okay? Again, the idea here is that you have components of vectors in the x and the y direction, and you're putting them back together. Last time we looked at this, we kind of took vectors apart, didn't we? We took vi and we multiplied it by cosine theta to get vix. And we multiplied it by sine of theta to get viy. We took our overall velocity and broke it into its components. Now we have the components, 33 and 329, and we're putting them back together to get our final solution. It's like having vix and having viy and coming back to get vi. Alright, quick look at a term, and then we're going to look at an application of this. First, the term mass. What do most people misconstrue mass to be?
Weight.
Yeah, and why is it not weight? Who can give me a reason why it's not weight? Why are they different, Lisa?
Because weight is how heavy an object is, and mass is how much matter an object takes.
Good. Now give me more. I want more of a reason. Why aren't they the same though? Why can't I just say, oh, I have a weight or a mass? Who cares? No difference. Why is there really a difference? There's one thing you have to think about.
Because there would be two objects that weigh the same but are different sizes.
No.
Alright.
You need to finish that statement with another, these are 3 more words on there, or 2 more words on there. 3 more words, it would make sense.
Mark out.
James?
Well,
Close, Lisa, very close. You're right there.
you know, gravity varies, so weight is really a force, and mass is a measure of how much stuff there is in the thing.
Yeah, gravity varies. That's the key you have to mention, okay? Gravity varies on Earth, on the Moon, on Jupiter, at different heights. Believe it or not, if you're at a different sea level, a different altitude, gravity varies. We'll talk about that later in the year how it works. But the idea is that your weight is a function of your location. The mass is not. Mass is a standard number that you have. You can change mass by exercising because you sweat and your molecules and the matter gets evaporated into space. That's how you lose mass. Okay? In effect, you lose weight also. But your weight is a function of location. Depends on the planet, depends on your altitude, it depends on everything. A lot more than just that. Whereas the mass is the amount of matter. So that was right. You're absolutely right. The amount of stuff or the amount of matter that you have. Okay? Now, let's talk about the idea of mass as a measure of inertia. Okay? Mass as a measure of inertia. This is going to be a little bit weird. You have to stretch your mind during that. Okay? What does inertia tell me again? An object will only move if it's acted upon by an... Yeah. So let's take a moment and think about an example. I'm playing golf. Okay? And on the tee I've got a golf ball. But on the next tee, Luke happens to be at the same driving range. He's like, you know what, Mr. Hill, I'm going to joke around. I'm going to put a baseball on the golf tee and try and tee off on a baseball with a golf club.
Been there.
Been there, probably done that, yes. So he's got, and be careful, we're not hitting a golf ball with a baseball bat. I know you've probably done that before.
Oh, yeah.
I'm talking about hitting a baseball bat.
Story about that.
Hold on, after you can talk. Give me a second. So Luke is next to me, and he's got a baseball there, and he's hitting the baseball, and I'm next to him with a golf ball. Clearly, which one's going to go further? The golf ball, because it's got less. It's got less mass, really, right? So think about it. Even if Luke and I, say we have the exact same swing, hypothetically, which we probably don't, but hypothetically we apply the same swing, so it has the same force and whatnot. Okay? Now, this is golf, not baseball. Let's be careful. So we have the idea that the same force is acting on the object, but the golf ball goes further. The golf ball goes further clearly, it gains more velocity because it had less mass or it had less inertia. Think about it. If an object has less inertia, it's easier to move it because inertia is a measurement of what it takes to actually get the object going, right? Inertia tells us, well, you know what? You can't move unless acted upon by an outside force. So if I apply the same force to two different objects, one moves a lot faster because it has less inertia, really. It's inertia that's keeping it at rest. So mass is really, a measurement of inertia. A measurement of inertia. So an object with less mass technically has less inertia. Is that clear? Okay? So they are directly related to each other. Luke, you want to tell your story real quick before I do one more thing?
We don't have enough time.
All right, we'll see. Then we'll check. So let's take a look at an application of this. Anybody ever wonder how seatbelts lock into place?
Oh, no, you hit the brake.
You hit the brakes and suddenly the seatbelt locks into place and you're like, what is this happening for, right? Okay? How does that work? Okay. So can I get someone to read, please? Nice and loud. Read, Tori, nice and loud for us.
Seatbelts use the laws of inertia to work properly. Once the brakes on a car are applied, the mass into the seat slides forward, which causes the rod to pivot. This causes the ratchet to engage the rod and stop its rotation. If the ratchet cannot rotate, then the seatbelt is locked and will hold the person in place.
So imagine you've got this mass underneath your seat, and it's in a little chamber, and the mass is free to slide forward and back. When you hit the brakes on a car, don't you fall forward right away, everybody? Right? That's what always happens. So what's the mass going to do? It's going to slide forward. Well, look at the mass. The mass is attached to this pin connection right here. When it slides forward, now you can see the rod. See the rod is pitched now? It's at an angle. So when the rod turns at an angle, it locks. It engages with this ratchet right here. When it engages with the ratchet, it locks the ratchet from moving further this way. So it can no longer rotate, therefore this is locked. Isn't that kind of cool to think about? There's no electrical work involved whatsoever. You're using the laws of physics to save your life. It's not electrical at all. It's just a mass sliding forward to lock and engage. I think today they have electrical backups and faulty and things in place in case that didn't work. Okay? But that is the idea behind a seatbelt locking. Let's talk about one last thing.
I always was curious how that works. I always just
I'm glad I can clear up that.
I always pull it until it had no more belt to give it. I just pull it like
The thing is, when it locks, and you ever try to pull on it when it locks, you cannot disengage it. But if you let go, what happens? The ratchet releases the pin connector. When you're letting go and giving it more so that you can then pull on it, what's happening is the pin is then turning back and the ratchet is now free to move. Okay? You can think of the word gear if the word ratchet is weird. Equilibrium. Equilibrium. We've talked about it, let's just define it. The state in which the net force on an object is zero, or there is no change in the body's motion. No change in the motion. Tell me, people. Am I changing motion right now?
No.
I'm not, because the net force is zero. Now, don't answer the question yet. Wait till I start moving. Wait till I start moving. So imagine I'm moving already. Am I actually changing motion?
Yes. No. Yes.
The
No.
answer is no. I'm changing position.
Well,
But my motion is
once you
constant.
started moving, your motion.
And that's why I said we need to specify again. Once I started moving, I am moving with a constant velocity. I'm moving at the same rate, aren't I?
Well, I had
So
to
I'm not
observe that you
changing-
accelerated.
But if we were to
I'm
start,
not changing motion, I'm changing position.
but if we were to start from when you were here, then you.
Absolutely. Absolutely. But listen, once an object is moving, and it's at a constant velocity, and you hit cruise control in your car, you are setting up equilibrium. That's what you're doing. You're balancing the friction between the air and the tires and the gears with the thrust force that the car provides forward. There's a complete equilibrium at stake. That's what a constant motion is. That's what cruise control is. You are a force balance. So next time you're at cruise control, you know what's happening. You moving forward, that force the car is pushing is equal and opposite the resistance that the wind is providing and that the gears are providing and that you're losing in heat energy or friction internally. Okay? The overall friction that is lost is being accounted for by the push of the car. And they are in equilibrium. That's why you're moving at a constant rate.
So would that depend on the size of the car?
Sure, the size of the car, the shape of the car, the temperature, the humidity. There are a myriad of factors that would affect it there. Okay? So what we can say is the following. Let's write a few things down from this. And these are some statements we're going to make. When F net, when the net force acting on an object is 0, we have equilibrium. I'm going to write it up here actually. When we have equilibrium, the net force is 0. When the net force is 0, that means the acceleration is 0. Okay? Remember the other day, if there's no force net, there's no acceleration. That's the cause. And if there's no acceleration, the velocity is a constant. So either, I showed you just 2 examples a moment ago, I'm standing still, I'm constant, or I happen to be moving, but I'm moving at a constant rate. Okay, so these are the 3 things that result from equilibrium. You have homework tonight and this weekend. Okay? Here's your homework. I'm also going to email you a video to watch this weekend. You have 4 days. You better do it. It's the whole video on section 4.3. We're not going to do 4.3 in class. So when you come out on Monday, we're going to talk about 4.3. But I'm going to record a video for that this weekend. And you're going to look at it, okay?
Is it only for like 20 minutes that we make it?
Yeah, it's only, my videos are like 12 minutes at most, okay? I mean, maybe 15, but usually it doesn't even happen.